I guess we kind of got to 6.2. There's a few other neat things, but we ran into this word problem of population growth or radioactive decay, kind of the same word problem over and over again. Okay, so there's one more kind of word problem in 6.2. There's only 2 problems assigned. They're at the end of your book, but it's about Newton's law of cooling. So I like this one. It's Newton's law of cooling. Again, I want to introduce it with with an English sentence. So the English sentence is the rate at which, sorry, it's almost a paragraph. The rate at which the temperature, and I'm going to call temperature capital T, the temperature of an object changes over time. And by the way, I'm going to call time little t. So those are my 2 variables, capital T and little t. They're 2 different variables, kind of like y and x, I guess. The rate at which the temperature of an object changes over time, watch this, is directly proportional, very similar sentence, directly proportional to the difference in the temperature of the body, or I called it an object, the temperature of the object and its surrounding medium, and its surrounding medium temperature, which I think we're going to call M, which is a constant.
So M would be the temperature of the medium?
Yes.
Okay.
Yeah, again, that's English, and I used to get C's in penmanship when I was a kid. Penmanship?
Mm-hmm.
You ever heard of such a thing?
Yes.
Yeah.
School.
Anyway, so I'm sorry for my C's in penmanship. But I just tried to write quickly. But I read it to you, so I think you can understand. The rate at which a temperature of an object changes over time is directly proportional to the difference in the temperature of the object and its surrounding medium. That's an English sentence, and I think I could write a DE from that. I think I can write the rate at which the temperature changes over time. Don't you think that's right? The rate at which the temperature changes over time is directly proportional to, but now it's directly proportional to the difference in the temperature of the object and its surrounding medium, which would be
T minus M?
good, capital T minus M. And then, that's awesome. And the variables in this problem are capital T, the temperature of the object is changing, little t is time, K is a constant, and the temperature of the surrounding medium is going to be a constant. We don't want that to change. That's a more complicated differential equation. When you take differential equations, the course, maybe we can do that, but in this class we'll just keep this constant. We'll keep this constant. We won't let it fluctuate. What's this? Here's what this says. Let's say my refrigerator is 36 degrees. That's my refrigerator. And I think that's M. I'm going to call that, my refrigerator is my environment. And I find this old hot bottle of water that's 80 degrees. And so at T equals 0, I have this hot bottle of water, which is 80 degrees, and I stick it in the refrigerator. So initially, at T equals 0, the 80-degree bottle of water is 80 degrees. It's a hot bottle of water. I stuck it in the refrigerator, whose medium temperature is 36 degrees. Now, the rate at which it cools, the rate at which the temperature changes, is directly proportional to the difference. So when there's a large difference...
Would we have to have a little t somewhere in that equation since it's over time?
No. We'll get one when we integrate. We'll mold the dt over here.
Okay.
And then we'll integrate and we'll get a t.
Awesome.
Right. the rate at which it cools is directly proportional to the difference. So when there's a big difference, like that maybe, or bigger if it was hotter, when there's a big difference in the temperature, the rate at which it's cool is going to be pretty big rate. What that means is that when the first few minutes you put it in, it cools rather drastically. But after sitting in there for 10 or 20 minutes, or 30 minutes, or 40 minutes, or whatever, you know, I mean, the rate at which it cools, as the temperature of the bottle of water approaches the temperature of the surrounding medium, that difference is less. When that difference is less, the rate at which it cools is less. And so it starts to cool at a lesser and lesser rate, which is the slope of the tangent line is sort of the rate. Are you guys okay? Mm-hmm. And I think what happens is it kind of approaches this like an asymptote, don't you think?
Yeah.
I mean, the hot bottle of water maybe never really reaches 36 degrees. Actually, probably does after a long time. It just, well, according to the math, it never really reaches 36 degrees. For all intents and purposes, after a couple days, it's 36 degrees. It's 36.001 degrees, you know. So does that make sense? First of all, I'm trying to make sense. Because I kind of like to try to make sense out of the physics a little bit and the math and the way the words, what the words mean. The rate at which it cools is proportional to the difference. So when there's a big difference, it's cooling at a fast rate. When there's less of a difference, it's cooling at a much slower rate. Right.
It's still kind of weird that there's still no lowercase t because we're dealing with two constants and the dependent variable.
Well, again, you're staring at the differential equation. Okay, we're about to solve that differential equation. I sort of skipped that part. I just wanted to talk to you about the concept.
Okay.
No, see now we are going to solve this differential equation. Let's solve it. And the k and the m are constants. The variables are capital T and little t. I think we should separate and integrate. What do you want to say?
I was just curious. What happens if we flip the two? The constant was 80 degrees and the temperature of the bottle was 36.
Yeah, you know what? So this is called Newton's law of cooling, but it works for heating. It works for warming. I mean, it really does. It's called Newton's law of cooling, but it works both directions.
So that would be positive instead of negative, right? Warming.
Well, it's still the difference in the difference. No, I'm not going to change. No. This is my model. This is my paragraph. It leads to this. But then, and then we're going to solve this dE. Here, let's solve it real quick. It's easy. You ready? I'm going to separate and integrate. So I'm going to put the dt over there. I'll just do this a little slowly here for a second. So if I put the dt over there, now let's see. I want all the capital T's over here. Any suggestions? Divide by the whole parentheses. Good idea, right? You can't really get it out of the, so you got to divide by t minus m. So you're right, dt over t minus m equals k dt. Yeah, this is cool. This is going to be a lot like the last problem, but a little different. In other words, a lot like the population problem, but a little different. We integrate both sides right now. Again, we got a lot of letters on the board. But the variables are little t and capital T. So when over on this side is the easy side, you're right. Integrate with respect to t, kt plus c. That's what we did last problem, by the way. And then on this side, it's kind of easy. The m is a constant, and the integral of this is? It is the ln. Technically, maybe you're doing a little u substitution. So this is u, and then du is dt. So it's really a 1 over u du is all it is, and so it's the ln of t minus m. It's the ln of t minus m. That's what that integral is. It's pretty easy. Okay, we're trying to solve for capital T, I think.
We'd have to add a constant to the other side too, right?
Okay, what do you mean? Hold on.
ln t minus m plus c.
Okay, now hang on. You didn't say that when I did it before. Maybe you did it. Anyway, hang on. We talked about how we could add it. You should, yes, add a plus c here, but then we would add that plus c over into that plus c and just call that plus c.
Okay. All right.
Remember that little conversation?
I do, just didn't know if it still applied or not. So.
Yeah, it applies on all these. When we separate and integrate, we integrate both sides. We separate and integrate. We integrate both sides, and I quickly got in the habit of not putting a plus C on this side because of that idea.
Okay,
Yeah.
all right.
Yeah.
So this is going to be almost exactly like the previous.
It sure is. What? Okay, so now we E both sides. And what do you do on this side? You guys have done it 2 or 3 times now. It's e to the kt times e to the c, which ends up being c to the kt. Now what about on this side? The e and the log cancel. You're left with the t minus m. So really, to get t, there's one more move. Add m. So here I am writing it like that. Actually, the truth is I tend to normally write it, with the m in front. You guys know about commutativity, though. It doesn't matter. This thing plus m is the same as m plus this. But yeah, cool. Dude, we solved the dE. And we have the model for this Newton's law of cooling. The temperature of the object will change like this. Right. Oh, and if you remember, this was the differential equation. This was the differential equation. We did a little calculus. But now, when we see these word problems, we tend to jump right on this and do a lot of very algebraic word problems. The calculus has sort of been done for us already. By the way, maybe you should memorize this is the answer, or be able to calculate it if you need to anytime. Similarly, for that population problem, you should memorize kind of memorize that model, Maybe this one for Newton's law of cooling. Okay, so now, can we do a problem? Okay, let's do a problem. And like I said, I'm going to get rid of all this. This was the idea behind it. That was the dE. We solved the dE. We ended up here. So now all I really want is this. And I want to write up a cool word problem for you. And here's a cool word problem for you. This on the CF campus, building 7, room 112, always remains a constant 52 degrees Fahrenheit.
Too cool for school.
Good. All right. So that's why I'm making this up. It's not really. We're in this room. It's not quite like that. In fact, I'm sweating. But it remains a constant 52 degrees Fahrenheit. So one day at 12:15 on Friday, a student found the dead body of their professor. Dead body.
James, what do you feel?
And of course, that student was a calculus student, so the first thing they decided to do was take his temperature. So the temperature of the dead body, the temperature was, hang on, the temperature was 64 degrees Fahrenheit. So then they, so then they called the cops, and then the cops came and they got there, 2 hours later. No.
Probably.
I shouldn't make fun of cops. 30 minutes later, they got there 30 minutes later, and they took the temperature. The temperature was, this person had died in this room, and their body temperature was approaching the temperature of the surrounding medium, right? The body temperature was approaching 52. Anyway, 30 minutes later, it had dropped to the temperature was 58 degrees Fahrenheit. So what the question is?
How long has he laid there?
What was the time of death? What was the time of death? This is a good
Oh,
forensics
gosh.
problem. What was the time of death? And then we can continue.
10.5 hours.
Yeah, right. Good guess. It might be
Okay.
a while.
Huh.
Although the thought process of that student, we take his temperature and a thought process.
Yeah, that was just very smart. All right, so we're using this model. This is our equation, and what's m?
It's 52.
And m is 52. So there's no doubt about that. In fact, let me just write down some notes here. So m is 52. Okay. Now, there's some other piece of information here. Now, I think we should, again, we can scale time however we want. I think it's smart to make that 12:15 t equals 0. I think that's when this problem should start. Although, you know, maybe, I mean, what's really happening is somebody killed this guy, or he died of natural causes, we're not sure. But this person died, and his body is... What was the temperature of this person before he died?
98.5.
98.6. He was a healthy person with a temperature of 98.6.
Okay.
And then he died, and his heart quit beating, and his blood quit circulating, and he began to cool at a rate proportional to the room he was in.
Are we using 98.6 as an assumption?
We will, but it's a fact. If he's a person, it's 98.6. If he was a healthy person, it was 98.6. It's an assumption, yes.
Okay.
Okay, hang on. So he died at 98.6, and then he started cooling. So, you know, you might want to say, well, the time of death is t equals 0. And I don't want to do that because I don't know that time of death, you know?
Mm-hmm.
So, I want to label something I know, t equals 0. So I'm calling t equals 0, 12:15, and what was his temperature? 64, thank you. So then what happened? 30 minutes later, that was 12:45. By the way, you want to do this in minutes or hours, it doesn't matter, as long as you're consistent.
We should do minutes.
We'll do minutes, let's do minutes. So it's 30 minutes later, and then what was his temperature? 58?
Yeah.
Okay, guess what? I think these pieces of information help you find C and K, right? Like normal, like we've been doing. And then the ultimate question is, what was the time which was before 0, the time of death? So I think the ultimate answer is going to be a negative value of time. That's okay, before 0. So the ultimate question is, what was the time when his temperature, when he was still alive, which means his temperature was 98.6. So I read the word problem, this is the information given, I get it organized, this is the question I need to answer, and it's not that hard, it's a bunch of fun algebra again. Let's do it.
So C would equal 64.
Oh, remember how we talked about, timeout. So remember how we talked about that C is always the initial value? You know what? That's the way it was with our other equation. It isn't really like that with this equation.
That's right.
Because of the M being involved, it's so C,
So
we got to calculate C.
Okay.
Yeah.
It's not too hard, but don't assume it's the initial value. That's not right on this example. It's not right. So what do I do though? But you're right. I plug in a 0, and I get 64 into that formula. This is 64. What's M? What's M? 52. And then I plug in a 0 for T. Are you guys with me?
Yes.
Okay, cool. And then that's e to the 0, which is 1 times C, so it's C. And then I move the 52 over, so I guess C is 12, huh? Cool, that's cool. All right, and that was that piece of information. That helped me find C. I think this next piece of information will help me find K. All right, here we go. Let's see, 58 is the temperature of the body. 52 is M. C is 12. E to the K, I don't know K, but I'm going to plug in 30 minutes. Again, it's that formula. It's this formula.
K is equal to L in 1/2 over 30.
All right, let me see. I'm going to subtract this. Subtract the 52, that's a 6, equals 12. 30K. He divided by 12 and got a half. That's interesting. after we were dealing with all those half-lives. And then you take the log of a half and you divide by 30, and that's K. Just did some very quick algebra to get K. We could make it a decimal or just leave it like that, to tell you the truth. It might be fun to see what the decimal is. Can you go ahead and tell me the decimal?
I got negative 0.023104906.
Okay, thank you. Again, for accuracy, I would like to not round this number. This is an important number not to round, I think. But I think we found C and K. I think we've got the model now. The model is T equals 52 plus 12 e to the K. I'm going to write natural log of a half divided by 30 times T. I mean, this is the model, and I can answer any question they want. You know, they might want to know, well, what's his temperature in 10 minutes? Or what's his temperature in 1 minute? Or, you know, they might have all kinds of cool questions, but what is our question?
Okay.
Find the time when his temperature was 98.6. That's our
Right.
question.
Right.
So we plug in a 98.6. And we try to solve for T. This is going to be interesting. I might need this. So you subtract 52, 46.6, divide by 12.
I got negative 58.719.
Minutes. Okay.
Hold on.
Right, hold on. So what did I do? I subtracted, I divided, did I subtract that?
Yeah.
Yeah, 46. And divide by 12, which is not nice. But now I'm going to ln both sides. Do you guys see me? I mean, it's getting a little weird, but it's okay. And again, I kind of tend to pick up my calculator at the end of the problem. So I kind of work with this. I got the ln of this, and it equals it over here. It kills the n, and it leaves me with the ln of a half divided by 30. So I'm going to multiply by 30 and divide by this. So I see this as my final answer, and then I go pick up my calculator. I don't know how you guys, if you like to think like I think, but there it is. You know, I did all this algebra. And then I go pick up my calculator, and I hopefully type this all in carefully, and he already told me 50.719. 7.72 minutes. Yeah, and I won't care about the seconds. I think what I'll ask is for you to round it to the nearest a minute. So that would be 59 minutes. Hey, did it come out negative? It should have come out negative.
Yeah, mine
Yeah.
came out negative. I
Okay.
was just about to ask about that.
Okay, good. It should have. Remember this was before 0. Remember? So it was negative 59 minutes before 0. And if 0 was 12:15, when was this?
11:16.
11:16.
11:16 a.m. Oh shit, that was 13 minutes ago. I'm still alive.
Never forget.
Cool, I think I'm all right. This is really just a work of fiction. But I was worried for a minute.
Well, at least we'll know the math next time, right?
That's right. Plan this a little better next time. Are you guys okay? It's a classic, cool problem. Again, it's a bunch of algebra. It's not that hard of algebra. It's E and log algebra. But it's organizing the data from the word problem, figuring out what's given, what are they asking for, and how to rescale things is helpful. There's only 2 of these in the homework. At the end of 6.2, there's 2 Newton's law of cooling problems. You should do them. They're probably not as interesting as mine, but the math is probably the same as mine. The other thing I want to say is that you could head on into 6.3. I mean, there might be a few other ideas in 6.3, but the beginning of 6.3 is separation of variables. Well, you've been taught that now for 2 or 3 days. So you could ease into some 6.3 homework. It's solving DEs by separating variables. So I'll see you next Wednesday, huh? Okay, thank you very much.